So today in the last lecture we have seen some function, basically one function which was very useful in the as a biologist to you using the Python programming language. Today we are going to deal with ODEs. What exactly is this ODE? Well, I'll tell you what exactly is a ODE, but before telling you what exactly ODE is, I'll tell you some caution. ODE is a very deep mathematical thing. So today what I'll try to do, I'll try to make it as funny and as simple as possible for you to make you understand this complex mathematical thing to you as a biologist, so that you understand it and you could implement it into some real life scenario whenever you face this. Also we'll see some Python related stuff related to this, so that we also understand math about it. Also we understand how to code the things related to ODE. Now picture this, you are a biologist on a quest to decode the secrets of life through the mystical art of ordinary differential equations, the ODE. Hold on to your lab goggles, because in this uproarious kite will unleash the power of Python, friendly neighborhood programming language, to wrestle ODEs and tickle your funny bone while exploring the wild world of biology. I hope you are going to find this complete lecture very funny. I've tried my level best. Now, going ahead, after exploring the wild world of biology, if we go ahead, we are going to divide it into several steps, in which the step 1 is setting up the lab environment. We'll call it lab environment. Before you dive into the mad science, ensure Python has crashed your computer party. Head to python.org and holy grail of Python downloads. Once you have successfully summoned Python, it's time to summon your trusty sidekicks NumPy, SciPy and matplotlib. Again, make it clear for you: NumPy, SciPy and matplotlib. Command your terminal with mighty pip install NumPy, SciPy and matplotlib. Spell and behold, your lab is equipped for epic number of crunching ODE deciphering and data visualization. The ODE, it is step 2. The ODE eureka moment. Ever dreamt of modeling the explosive growth of population? Have you ever dreamt of modeling the explosive growth of population? Dream no more. In Python, as simple as brewing a cup of coffee, or even maybe easier. Behold the legendary ODE function. So we have this particular code for Python, which is import numpy as np. You can import it as np, ne, ns, whatever you want, but in general form we generally import numpy as np. Remember, in numpy everything should be in small. After this, we are going to define ODE function, in which we'll define a function by writing def. Whenever we want to define any function, we'll start by writing def in front of it, and we are defining a function which is exponential underscore growth, and will give 3 parameters. First parameter being y, second is t, and third is y, t and r. After that, we'll have another variable, we'll write is as dy dt, something familiar you have learned in mathematics in some of your school days. Don't worry, just write it down for the time being. Dy dt equals to r start y. Whenever you want to write multiplication in computer don't understand multiplication as a symbol. The moment you go symbol of multiplication, it will act as x. So whenever you want to multiply anything, we generally write r star y. So this multiplying r with y, and then we'll return dy dt. With this sourcey, you can predict how fast your pet bacteria will take over your fridge. The step 3 will be initializing chaos and time travel for our population party. You must choose the starting population and the duration of your simulation. Imagine starting with a single lonely bacterium and traveling through time for 5 units, whatever those units may be. For this, we are using this particular Python code in which we are using initial population y0. We in math we can also call it y0, it's your choice. Y0 equals to 1. Then we are giving time points, which is t equals to np. We are using a particular function of numpy, that is np dot line space, in which we are giving 3 parameters 0, 5 and 100. Now you have to prepare yourself to witness the rise and fall of the microbial empire. We'll go to step 4. We are going to unleash the ODE solving beast now. The moment you have all been waiting for, the solving of ODE equation and watching populations rise and fall like empires of old. Python's SciPy library is your trusty steed. With the mighty ODE function by your side, don't forget to choose your growth rate wisely. For this, again we have a Python code that from SciPy dot integrate. Again, you must have heard this integration in your classrooms in some class 11th, class 12th level. So we are again taking that integration from SciPy. It has already created some functions for it. We are trying to import ODEINT. Now, kind of given and a particular variable growth rate, we say let's assume it as 0.2. Now let the ODE solving adventure begin. The solution would be equal to, we are again taking a variable solution, which is equal to ODEINT, that is again a function of SciPy, we have seen it. ODEINT, the function uses parameter of exponential growth, comma, y0, comma, t, comma, arguments, in which the one argument is growth rate. So you have given all this thing to ODEINT. I don't want to do integration. I don't want to go down into the copy and I take a pen and I don't want to do that. As a biologist, why should I be? You create a function, let me utilize it. So this is what computer science is for you. The spectacle of visualization to make sense of this biological soap opera bring in the grandmaster of visual storytelling, that is the matplotlib. This is the step 5 I'm talking about. Now we have seen the population. Now we are going to plot your pop in all its glory. For this, we have this particular Python code, which is import matplotlib.pyplot as plt. You can call it as tlt, mlt, hnt, I don't care. We generally import is at plt, standardized format. You can name it as anything. After this, we are going to prepare a grand finale. Yes, literally a grand finale, wherein we could visualize things, we could see, we could analyze, we could experience the power of ODE in the biology. What we'll do, we'll use plot, in which plt.plot, it will plot. In one label it will plot t, in another label it will plot solution, t and the solution. X label is the t time, y label the solution, that is population. So time and population, it will draw time and population. The title we can give as exponential growth, the epic saga, and we'll say plt.grid is equal to, so that we could also see the grids in the plot. After doing this all things, we'll say plt.show. Whatever I have given you the instructions, please at least show it to me. Cue the dramatic music as you watch the population roller coaster. After this, we are having step 6, in which we are going to explore like there is no tomorrow. You have now conquered the hilarious world of Python, ODEs and biology. As you gain more confidence, venture into realms of complex biological models and scrutinize your results like biologist with of course a magnifying glass. The laughter never ends in the world of science. But wait, there is more. There is more. Behold a new comedy act. Let's give it as a title as Python Contagious Comedy, the disease spreading extravaganza. You, the unsuspecting public health researchers are about to embark on a quest to demystify the enigma of disease spread. Join me on this side-splitting journey through Jenny world of Python-powered ODEs as we unveil the secret of disease transmission. In this another example that we are taking, the step 1 would be setting up of the outrageously hilarious environment before diving headfirst into the riotous worlds of disease modeling. Make sure Python is your partner in the crime. If not, rush to python.org and the virtual circus of Python downloads. Now, prepare for the slideshow by summoning up the essential libraries. We have already done it. The first thing that we are going to do is the pip install numpy, scipy, matplotlib. I'll hold you for a second here. Why? Because whenever you are going to write pip installed, remember, I'm again and again telling you this thing just to make sure that you write your codes without any even a single error. Whenever you are writing pip install something of this kind, and in the Jupyter notebook, start with exclamation sign, then only it will go to your kind of OS thing, and it will know that you want to install certain things, otherwise it might throw errors at certain time. The step 2 would be the ODE that will make you laugh through model disease spread. We present the legendary SIR model. I'll explain this SIR model for you. The susceptible, infectious, recovered. Behold the ODE that will leave you in stitches. The first thing that we are going to do here is we'll import numpy as np. That is the most necessary thing. Anyhow you have to do it. You have to import the numpy as an np. After this, you will define the SIR model ODE function. Which model? SIR model ODE function. We will write it as DEFSIR in capital underscore model, and we'll give it some parameters which is y, t, beta and gamma. But you can choose the name as per your choice. It's my function I have named is a SIR model. You can create your own function, you call it as hand model, I don't mind, and which SIR is equal to y, and again I'm giving another variable dsdt which is equal to minus beta into s into I. Oh, a bit of maths, but don't worry, this all things are very easy and going to be get solved by the Python. Python handles this all integration things for you. If you go in, again as I've already said, if you go in by a rough copy and a rough pen, drawing it, starting with this symbol of integration, it will actually be a very painful situation. But this dsdt is kind of mathematical function for the time being, consider it, is equal to minus beta into s into I, and didt is equals to beta or beta into s into I minus gamma. You all know this already. After this we have drdt. This all are variable name, you can change it as per your convenience. Remember, more convenient in writing it in this form, because in mathematics also we write it in a similar form. That is why I have written it like this. It's your choice, you can make it, you can change it, you can have it according to whatever your suggestions or whatever you feel good writing it down, like whatever variables you feel good writing it down. Okay, after we are having drdt is equal to gamma into I, and in the end my function will return dsdt, didt, drdt. Let me explain what exactly is return is. What exactly this return is. Whenever we are returning something, we try to find out. So it's like whenever I'm giving certain function, in the end it will tell you what exactly you are supposed to do in the function. For example, if I have a function that adds up two numbers, I have a number a, I have a number b, I want to add those number, and I want the result the sum of two numbers. The A is 2, the B is 3, the sum should be 5. So in the end I should return 5. That is something that I require, isn't it? Similarly, we are returning ds dt, di dt, dr dt here, because that is something that we want in return. That is something that we want to analyze. That is something that we are having in head to analyze things. Again, let's get to comedy. In this comedy, beta is the star of the show, representing disease's charisma, and gamma plays the role of recovery magician. Again, the moment we go to the step 3, the step 3 is the hilarious setup. In this, just get ready for a laugh riot as you set up the initial condition for the susceptible, infectious and recovered individuals. Time travel for 200 days. Yes, why not? We are having the power of computers. So we'll use this Python code. We'll say initial condition as not equals to 0.99. That does mean 99% of the same population is still sane. After that, we have 0.01. That does mean 1%. Remember, 1% is infected. Watch out for the sneeze. We have R naught, which is 0.0. Nobody has escaped the chaos. Time point for the epic saga. Now we are dealing with time here. For time, we are giving t equals to np dot line space. Np is a numpy library, if you remember, and then the line space we are giving 0, 200 and 1000 as its parameter. Now we'll jump into this step 4, which deals with entering the circus ring of ODE solving. Now it's our show time. You use SciPy's ODE function to solve the SIR model ODE, and again let the laughter begin. We have this particular Python code for this, which start from importing from SciPy integrate import ODE. Same thing as we have done earlier. We are using the integration from SciPy. They have already done it, we are just importing it. After this, we are going to give a disease parameters, which is Q to the diametric music, and we are giving beta is equal to 0.3. Transmitter, the transmission rate gamma is equal to 0.1. Recovery rate 0.3 was transmission rate, 0.1 was recovery rate. Now watch as the ODE takes center stage solution. For this, we are using ODE function. We take parameters as SIR model, and after SIR model we are giving parameters S naught, I naught, R naught, T, and we are also giving the argument as beta and gamma. This is the step 4 that we are talking about. After this, we have a step 5, in which the Reuters visual spectacle. To witness the disease spread extravaganza, you have to gather your audience and create a short plot of what an English. After this, we are going to import a matplotlib.pyplot as PLT. Same thing, certain similar things that we have already done in the earlier code. Is just I'm showing the code again and again and again and again, so that it kinds of inscribe gets fitted into your brain. You understand things again by going through this matplotlib again, the SciPy again, the particular modules again and again, so that you know, you understand, okay, this was the thing. Again, it is the same thing that I'm encountering. As a biologist, you already know that in our mind we have different neurons that are interconnected, and the more we read a thing, the more powerful memory it creates for you. I just want to create that powerful memory for you. That is why I'm again giving the same example, different example, but the same scenarios, kind of same files we are importing. Now roll out the red carpet for the visual masterpiece. We are trying to draw the figure by using plot.figure, in which we are giving figure size as 10 cross 6. We have plt.plot, in which we are trying to plot t as well as solution column dot comma 0. It has mean whatever it is, I don't care. The column, 2 columns, it says that I don't care what it is, but it should be of 0th index. It should be of 0th index. It can be from any initial till initial, infinity minus to infinity plus. but of 0th index column, in which we are giving the label as susceptible. After that we are plotting the solution. Again it can, the first phase or the row can go from minus infinity to plus infinity, but the column is first, which labels as infectious. After infectious we have solution column to the second column, which is kind of the label we are giving it as recovered. Now we are going to give this plt dot x label, in which we are giving time in terms of days, and y label as fraction of population. What x label is? X label time in days, y label fraction of population. Now we are giving this particular plot a title, that is SIR model. We have made this SIR model right in front of you. So the SIR model for disease spread, and it's going to be a blockbuster. That is why I have written the blockbuster. After this we are going to plot the legends. We are going to say grid is equal to true. That does mean give the grids to my plot, and plot dot show me the plot that I have created. After this you can see the plot. The step 6 would be continue our comedy exploration. Now you have mastered the art of modeling disease spread. Let your creativity run wild. Adjust the parameters, throw in some plot twist, and explore the world of disease control with Python as your trusty sidekick. You have completed 2 side splitting acts in the grand circus of Python and biology. May your experiments be uproarious and your quotes be even funnier. I've tried to explain it in a funny way. We have certain more steps that we can also think of. For example, we can think of as step 7, the unpredictable twist. Just when you thought the show was over, the world of biology throws you a curveball. Imagine modeling a population of narcoleptic kangaroos with an affinity for disco dancing. Yeah, we are dealing with some funny things. So with an affinity of disco dancing. Now Python's ODEs are here to help you bring this absurdly to life. For this we have a Python code which start with importing numpy as np, and we are going to define the ODE function for disco loving kangaroos. We are going to give as function which start with def keyword, so that we know it's a function. We give the name of the function as disco kangaroos. Let us name it as disco kangaroos. We are giving some parameters y, t and rave factor and again we are writing some mathematical function which is dy dt equals to rave factor into np dot sine. We are using sine function for 2 dot np dot pi. Whenever you are writing np dot pi, it takes pi as a value. So instead of defining pi is equal to 22/7, we generally take np dot pi, so it just take the similar values into t. So we are essentially writing 2 pi t here. After this we are returning dy dt. I know it's a bit of math, but you'll enjoy this the moment you plot this. Watch as this kangaroo groove to the beat of sine wave. Biology has never been so bizarre. After this we have step 8, which is setting the dance floor. You have to get ready to unleash the kangaroo party. Of course they are dancing. Set your initial condition and time span for this disco inferno. For this we have a Python code which initiate the rave excitement. Y naught is equal to 0. Time points for the ultimate disco experience, we have t is equal to np dot line space, in which we have 3 parameters 0, 10 and 1000. After this we have step 9, which is dancing with Python. Python is your dance partner once again. Use scipy's ODE function to make these kangaroos boogie like there is no tomorrow. I'm again repeating the same functions again and again. Neuron interconnection, remember. So from scipy we are using again the integration. We are again importing ODE and function, and we are again giving a rave factor which kind of adjusting for dance intensity. We are saying rave factor is equal to 1. We are saying dance kangaroo dance. The solution being here is ODE function, in which we have one parameter is disco kangaroos. We are giving y naught, we are giving t, we are giving argument args is equal to rave factor. Next step we are seeing the disco fever plot prepare for the most epic kangaroo disco party. And for this, we'll witness a Python code. So now we are going to look at this particular Python code, in which in this particular Python code we are seeing import matplotlib.pyplot as plt. We have already seen this. This is something it must have been inside your brain till now. So we are using this matplotlib function, and we are setting the dance floor on the fire with this plot. We are using two functions in the t and the solution. The t is in the x label, the array factor is in the y label. We are giving it a title as narcoleptic kangaroo disco fever. We are saying grid is equal to true, show me the grid and show me the plot. The science of laughter. You are officially joined the rank of biology's funniest comedians. I'm not sure. I've tried to make it as funny as possible. I know I'm not funny, but still. With Python as your comedic sidekick, you can model the quickest scenario from dancing kangaroo to roller coasters, populations, dive deeper into the world of biological ODEs. Explore new frontiers and let your imagination run wild. In the end, we can see the grand finale as the curtain falls on this comedy of ODE. Remember that Python is your partner in the scientific world of biology. It's full of surprises, and with Python, you are equipped to tackle them with your humor and curiosity. Keep coding, keep laughing, keep exploring the fascinating universe of biology. There you have it, a 3-act comedy extravaganza starring Python, ODE, and your boundless imagination. May your scientific pursuit always be a source of joy and discovery. With this, I end today's lecture.